Topic 3, acids and bases, from topic 3 in your textbook. The pH scale is a way to measure how acidic or basic something is. So things to note, that neutral is the middle of the scale, so 7 on the pH scale. Anything less than 7 is considered more acidic. The further away from 7 it is, the more acidic it is. Note, you can actually get something that has a negative pH. It is so acidic. However, most things stay within the range of 0 to 6 for acidic pHs. You can see here, something that's acidic slightly is milk. Coffee a little bit more. Tomatoes, the juice of tomatoes has a pH of about 4. Vinegar is lower than a tomato. A lemon is more acidic than vinegar. Our stomach acid is about 1, and a battery acid has a pH of 0. Anything that is greater than 7 is considered basic. Another way of saying basic is alkaline. You might see that. I'll try and use the word basic though. The further from 7 it is, the more basic it is. Just like we can go off the scale from 0, we can also go off the scale from 14. We could get something that has a pH of 15. Things that are slightly basic are blood. Baking soda is basic. Stomach tablets, so an antacid is a little bit more basic. Ammonia solution is about an 11. That is like a cleaning solution in your house, some ammonia. Soap is basic. Bleach is quite basic. And drain cleaner is very, very basic and something you would want to take care of using. So, remember, 7 is neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. The further from 7 you are, the more acidic or basic you are. Indicators are a substance that change color when added to an acid or a base. So an indicator will change one color if it's in an acidic solution and another color if it's in a basic solution. Here's 2 that we use in the lab. They're more of a chemical indicator. Bromothiamyl blue changes from yellow in something acidic to blue in something basic. Now note that it actually has different variations of its color as we move up the pH scale. When it's neutral, it looks a little bit green or tealish. Phenolphthalein moves from clear, if it's acidic, to pink or like this really hot pink, almost red if it is basic. We also have natural indicators, ones that we can find in nature. Cabbage juice, so if you boil purple cabbage and add it to acids and bases, it will change different colors. Litmus is found from lichen that kind of like grows on rocks and stuff. It is a plant and we've treated paper with it. So red litmus turns blue in the presence of a base. Blue litmus turns red in the presence of an acid. So this is the initial starting color of the paper. We have both kinds, red and blue. Physical and chemical properties of acids and bases. So how do we say something is an acid and how do we say something is a base? Like we said, acids have a pH less than 7, whereas bases have a pH greater than 7. Acids, if you taste them, like ones that we use in cooking, we definitely don't want to taste all of the chemicals in this world. Ones that are used in cooking taste sour, and bases taste bitter. So baking soda versus lemon juice. In an acid, blue litmus turns red, like I said. When we use litmus paper, we use both red and blue in the same sample. So my blue litmus turns red, but my red litmus is just going to stay red. In a base, my red litmus turns blue and blue stays blue. So note that their end color stays the same in both cases. Acids react with metals. Bases do not react with metals. When an acid reacts with metal, like if I put zinc into hydrochloric acid, I see bubbles. Okay. Acids have no feel, they aren't slippery or anything like that, whereas bases feel slippery. You can think about this because, remember, soap is a base. Acids and bases are both corrosive. They both conduct electricity. Acids will neutralize a base. If I add a base to an acid, it brings the pH closer to neutral or 7. If I add an acid to a base, it brings its pH closer to 7 as well. How do I pick out an acid? Its formula usually begins with an H. So H and then some other chemical formula. Something with an H in its formula, not at the front, is not considered acidic. Bases, typically their formula end with OH, like NaOH or MgOH. These are both bases. Again, some examples of acids and bases. Hydrochloric acid, sulfuric acid, nitric acid. You can see that H is at the front of each of their chemical formulas. Common acids we find around our home or in our life, lemon juice, tomatoes, vinegar, again, milk, battery acid, rainwater can be slightly acidic. Examples of base, noting that their formulas end in OH. Common bases in our house, baking soda, our blood is slightly basic, soap, like we said, and many cleaners. Acid rain or acid precipitation is kind of acids and bases in real life in the environment. How do we get acid rain? Well, sulfur dioxide and nitrogen oxides, so SO2 or NO, NO2, NO3. These enter the atmospheres from cars and burning fossil fuels. When they combine with water in the atmosphere, they produce acids and fall to the ground as acid rain, acid snow is possible. There can be acid in fog and in the clouds themselves. So anywhere that water would exist, really. So sulfuric acid is produced when SO3, sulfur trioxide in the atmosphere, joins up with one water molecule in the atmosphere. It makes H2SO4. Nitric and nitrous acid are produced when we have two NO2 molecules reacting with one water molecule. And H from one water molecule joins up with one, making HNO2, and the other H and the O join with the other to make HNO3. Carbonic acid actually forms this way too. CO2 in our atmosphere joins with water, making H2CO3, noting that each of these have an H to begin with. Most gases that lead to acid rain come from the burning of fossil fuels, such as coal, gasoline, natural gas, etc. Of course, we know that the products of combustion are CO2, but if we don't have just a perfect hydrocarbon where it was hydrogens and carbons, maybe it had a sulfur or a nitrogen in it. That's how we start getting these guys as byproducts. So what's the harm? What's the problem with acid rain? The big one is that it disrupts the pH of aquatic ecosystems. So rain falls, soaks into the ground, or runs off into rivers. Rivers feed lakes, or streams feed rivers. It basically starts to concentrate our acid, making it more and more acidic. This is not good. Fish don't want to live there. Things don't want to grow in an acidic environment. So we start killing off some of our species. Just in that same way, things don't want to grow in acidic conditions. So it'll reduce the yield of a crop and it'll harm the vegetation. So we may start to lose plant species because of acid rain. If they have a narrow niche maybe of pH they can thrive in. The last one is that it accelerates the decay of building structures and monuments. So a lot of older sculptures are being eroded over time by acid rain and acid buildup in our ecosystems. So how do we prevent this or recuperate from it, I guess? We can add a base to an acid to neutralize some of the effects of an acid. An acid and a base together make water and then a salt, which is just an ionic compound. Sometimes it'll make carbon dioxide, but not all the time. So for instance, vinegar and baking soda makes water. We see carbon dioxide, that's what makes it fizz, and a salt. When you have an acid indigestion, you would take an antacid like Tums or something of that nature, and it will also produce carbon dioxide as well. Another way that we can do this, neutralization, but on a bigger scale, is liming. Adding lime, which is calcium hydroxide, to lakes neutralizes the effects of acid rain. It's not really necessary in Alberta because the mountains contain so much limestone, which is calcium hydroxide, and it actually helps to neutralize on its own. When the acid rain falls, it's neutralized almost immediately. Lastly, this is almost impractical though, because every time it rains, we're introducing more acid into the ecosystem. So we would continuously have to be adding calcium hydroxide or lime. And this may have detrimental effects. Not only is it very costly, we're starting to perhaps maybe add too much. Who knows? So it's expensive is a big one and time consuming. And maybe there's other ways that we can go about this. So our governments got involved. They aim to reduce the industrial emissions put into our atmosphere. And by doing that, they'll reduce the amount of acid rain that would fall. So our government joined the Kyoto Protocol or the Paris Accord. So these are treaties between nations to reduce emissions of greenhouse gases. They've also enforced protocols within their countries. So vehicle emission standards, for instance, catalytic converters, they're in the exhaust system of cars. They remove harmful oxides from exhaust and convert them into CO2. This is done with a metal inside of them, and like platinum, rhodium, palladium, these are expensive, and so oftentimes catalytic converters can be stolen out of cars. That's become a bigger problem. But in general, what we're trying to do is just remove these two from our atmosphere. CO2 isn't as bad. It doesn't create as much acid rain as NOs and SOs. Last but not least, scrubbers can be used to remove harmful emissions from factories and power plants that burn coal to provide fuel for their plant. They absorb the sulfur dioxide, so SO2, that comes out in the exhaust before it is being released into the atmosphere. So some old scrubbers used calcium oxide. It absorbed, like again, this is lime. It absorbed the SO2, but it couldn't be recycled, so it produced a lot of waste. After the calcium oxide or the lime had absorbed the SO2, we had to remove it and put new stuff in. So a new system was designed, Cobra system. It absorbs SO2 and NOs, so nitrous oxides, and it can be recycled and reused. So when this stuff, I guess, is full of SO2 and NOs, they'll put some new stuff into the system, but they'll use this trapped SO2s and NOs within the old stuff to produce other important sulfur compounds for industry. So they'll make just sulfur or sulfuric acid for other industries. So they're recycling the sulfur dioxide that they actually capture. For practice, complete the learning guide for topic 3, acids and bases, in your learning guide booklet. There's some extra practice in our textbook as well if you're looking for it.